lecture 6. So, in this we will define what is a Poisson process. So, recall that, so there is a, you can specify a counting process, right, either by specifying n of t for t greater than or equal to 0, or the sequence S n or the sequence x n. We know how to go back and forth between the arrival epochs S n and the inter arrival times x n, right. There is a simple relationship, in particular right, that we know, and likewise S n can be obtained from the exercise using that. And also there is some statistical equivalence that we just proved between S n and the NTs, right. So, if you just go back to the proposition that we proved in the previous module, there is, if you, so this event is equal to this event, right. So, in some sense you can in principle get the CDF of S n, right. If you know the CDF of S n or joint CDF of S n, you can get the joint CDF of N t and vice versa, right. You can, so this relationship in principle gives you a statistical equivalence between N t and S n, right. So, in principle a statistical description of any one of these, you should be able to get a statistical description of the other two, right. So, if I give you x size, you should be able to go to S size, from which you can go to N t and so on, all right, or the other way. So, it is always a, so what is a convenient way to define, if you want to study a particular counting process, what is what is the convenient sequence to study, is it N t or is it S n or x n's, right. Well, it depends on the situation usually, and in the case of a Poisson process, which is perhaps the most elementary counting process, you can approach it when there are, I know at least 3 equivalent definitions, we will do 3 equivalent definitions in class. The one that has to do with this inter arrival times x n's is perhaps the easiest to understand, okay. So, we will start with that, but there are also equivalent definitions in terms of N t's or S i's, okay. If the sequence x i's or x n's, these inter arrival times are independent and identically distributed, then N t is N t is said to be a renewal process. Okay. So, this x n's, remember, is the amount of time that elapses between the n minus 1th arrival epoch and the nth arrival epoch, it is the inter arrival time. If these inter arrival times, of course, these inter arrival times are assumed to be non-negative, they are of course non-negative random variables, right. If these x i's are IID, independent and identically distributed, then we say that the process, the counting process is a renewal process, okay. It is a word, it is introducing a new terminology, okay. So, if x i's are IID, renewal process, okay. By the way, so I should make a remark that we throughout we assume that 2 arrivals occurring at the same time has 0 probability, okay. So, in all this we will assume that x n is greater than 0 with probability 1, okay. So, probability that interarrival time is actually equal to 0 has 0 probability. Okay. So, with with probability 1 you will have distinctly separated arrivals, you do not have two arrivals at the same point. Okay. So, this is something that we will assume throughout because it is little easier to deal with the it is technically easier, number 1, and number 2, in practice also I mean what are the probability of like 2 radioactive emissions happening exactly at the same time is practically 0, right. I mean you do not have in continuous time, you do not have arrivals at the same time. So, I think it makes sense to assume this. If this is not the case, if you have multiple arrivals at the same time, what you do is you put a different distribution on the number of arrivals at that come at a particular point. Okay, that is you can model it differently using a different random variable, which if a file comes to you with a certain number of packets in it, you can just model the number of files in the packet is with a different random variable. You can just say file arrival happens at this time and a bunch of packets come in that file or something like that, right. So, we will assume, so long story cut short, xn has there is no atom at the origin. Okay, there is no probability mass at the origin. Okay, probability. So, everywhere we assume that so this we assume, okay, probability that xi greater than 0 is equal to 1. Okay, this we will assume. Okay, for all I. So, that is what a renewal process is. And what is a Poisson process? A Poisson process is a renewal process with xi's exponentially distributed with some parameter lambda. Okay. So, in other words, so the density of xi is lambda e to the minus lambda x for x greater than or equal to 0, okay, equal to 0 for x less than 0. This lambda is a positive parameter, is called the rate of the process. Okay. So, what is a renewal process? A renewal process is a counting process in which the interarrival times are independent and identically distributed. What is a Poisson process? A Poisson process is a very special renewal process. So, the interarrival times are not only IID, they are IID exponentially distributed with some parameter lambda, okay, and this lambda is called the rate of the Poisson process. Okay. So, that is what it is. So, for a Poisson process, it is a counting process defined on positive time axis, where the arrivals occur IID exponentially apart. Okay. Any questions on this? Now, what is so great about this exponential distribution, right? So, we are taking saying renewal process means IID interarrival times. I am giving it a specific name when this interarrival times are exponentially distributed. I am calling it by a very specific name, Poisson process, and I have a chapter dedicated to it, right. So, what is so special about exponential interarrival times, and what is so special about the exponential distribution? Yeah, so it satisfies a very important property called memorylessness. The exponential distribution is memoryless. Let me just define this. Memoryless property. So, a random variable, so forget all these processes for now, just for the purposes of the definition, a random variable x, okay, so non-negative random variable x. So, random variable x is said to be memoryless if the probability that x takes value greater than t plus s given that x takes value greater than t is equal to probability that x takes value greater than s for all t comma s greater than or equal to 0. Okay. So, you are looking at some random variable x. Okay. In our case this x is an interarrival time, right. So, you are waiting for some arrival to come, right. So, the probability that you waited for t, right, you waited till t and there has been no arrival, meaning that the interarrival time has been bigger than t. Given that you waited longer than t, what is the probability that you will wait for a total time of t plus s, which means what is the probability given that you waited for time t, you will have to wait for another time s. It is the same as the probability that you waited for time s from the beginning, right, and this should be true for every t and every s. Okay. So, in some sense this random variable x forgets how long it has been, okay, that is why it is called memoryless. Okay. So, the fact that you waited very long time or very short time does not does not make it any more likely or less likely for an arrival to come soon. Okay. So, if x could model let us say a lifetime of a light bulb, right, the given that it's lasted I do not know 1 year, the probability it will last another month is the same as the probability that a new bulb lasts 1 month, okay, that is what we are saying intuitively. Okay. So, this is the memoryless property. Okay. So, we can easily argue that so claim you can easily argue this, if x is exponentially distributed with parameter lambda. So, which this means x is distributed according to the exponential distribution lambda. I hope you have seen the exponential distribution, right. So, which means that x just has that sort of a distribution. Okay. If x is exponentially distributed, then x is memoryless. So, you can easily prove this. You take the LHS, which is the probability that x bigger than t plus s given x bigger than t, this probability of a given b, right, this is probability of a intersection b over probability of b by definition of conditional probability, all right. Now, this is probability of x bigger than t plus s and x bigger than t, but the event that x bigger than t plus s is contained in the event x bigger than t, correct, because if x is bigger than t plus s, it is certainly bigger than t, right. So, this just becomes, so it is like probability of a intersection b when a is contained in b. So, a is contained in b, a intersection b is a, right, the smaller set, right. So, this should just be probability x bigger than t plus s over probability x bigger than t, and you have assumed that x is exponentially. So far I have not assumed anything, right, I have just manipulated the conditional probability expression. Now, I assume x is exponential with parameter lambda, then the denominator becomes e power minus lambda t, right, because this is the, so the CDF will be 1 minus e power minus lambda t, probability x less than or equal to t. So, probability x bigger than t will be e power minus lambda t, right. You go back from, you know the density, right, you can always calculate CDF and the complementary CDF, correct. I hope you can do this much. The numerator will of course be e power minus lambda plus, sorry, e power minus lambda t plus s, which is equal to e power minus lambda s, right, this cancels, this is nothing but the probability that, correct. So, this is true for all s and t. So, I have memoryless property, right. So, if x is an exponential random variable, then it is memoryless. So, if I give you an exponentially distributed, so if a light bulb whose lifetime is exponentially distributed, then if I tell you that it's this light bulb is really old, it does not mean anything, right, it is as good as the bulb is new. Of course, light bulbs in real life are not like that, right. But in this Poisson process, so this is what, so if you have this interarrival times which are exponentially distributed. So, let us say there is a bus process, you are waiting at a bus stop and a bus process that is going by you is a Poisson process, then the fact that you waited for a very long time does not make it any more likely for the bus to come soon, right, and of course, in the real world the buses do not behave this way, right. Also what can be shown is that among the continuous distributions, this exponential random variable is the only memoryless random variable. There is no, if x is memoryless, then it must be exponential. What we have shown is that if x is exponential, then it is memoryless, but the converse is also true. If x is memoryless continuous random variable, it must be exponential. Okay. So, you can add that as a remark, right. Remark can be shown exponential distribution is the only memoryless so in the continuous world. Okay. In the, if you are looking at the discrete world, discrete integer valued random variables, you can have a definition of memorylessness which is very similar to this, except the t and s will be replaced by integers m and n, right. In that case, for discrete random variables, you can prove that a geometric random variable is memoryless, and it is the only in that world. Okay. So, continuous world exponential is memoryless, discrete world geometric is memoryless. Okay. The way you prove that, so since I made this remark, you can prove this, you basically go like this. So, this step to here remains the same. So, essentially you have some sort of a functional equation, right. You have probability of x bigger than t plus s divided by probability of x bigger than t is equal to probability of x bigger than s. So, you turn that around. So, you have the this is the complementary CDF at t plus s is equal to complementary CDF at t times complementary CDF at s, right. Now, you go ahead take logarithm, solve this functional equation, you can prove that this you will get an exponential distribution. It is a little bit harder than the forward proof is very easy, I did it in 2 steps, 3 steps. The reverse proof also you can try. Okay. This, so maybe this I will leave as a homework. It is a little bit more involved, but I think you can do it. Okay. Essentially what I am saying is that you prove the converse of this claim that we have proved. Okay. You start with this equation that relates CCDF, the complementary CDF at t plus s is equal to complementary CDF at t times complementary CDF at s, Okay. You take logarithm, then the logarithm of the CCDF will be linear and you can get an exponential. Okay. Try doing this yourself, all right. So, that is why this Poisson process is so special, right. So, if you are looking at a Poisson process, the fact that you have not seen an arrival in a very long time does not make it any more likely or less likely to see an arrival soon. Okay. So, I said that I mean buses do not behave this way in general, right. What does behave very close to a Poisson process is in fact radioactive emissions. Okay. If you are looking at if you take a radioactive sample and count with a counter how many emissions do I see, the clicks of these counters, clicks of the counter will constitute very closely constitute a Poisson process. Okay. The inter arrival time, the time arrivals between any two clicks will be exponentially distributed and independent. Okay. This is a very good radioactive decay is very closely follows the Poisson process. The reason this is the case we will discuss later. Okay. So, in the bus stop example case, of course, it does not behave this way, right. Ideally, if you waited for a long time, you would like the bus to come soon, right. So, suppose the bus arrivals let us say they are uniformly distributed between 5 minutes and 10 minutes the inter arrival times. So, the time arrival between two buses could be anywhere between 5 and 10 minutes, let us say for the sake of argument. So, if I waited for let us say 8 minutes, I know for sure that there will be a bus in the next 2 minutes, right, just to give you an example, right. So, it makes it more likely in this case, but of course, the other extreme is also possible that you may have a small probability of the bus breaking down, which means the bus may not come for 2 hours, right. So, if you waited for a very long time, the chances are that bus is broken down and you will wait even longer, right. So, that is also possible, right. So, this Poisson process is in between, sits in that in between, it does not make it more likely or less likely to see an arrival soon. Okay. And what is more, this is the only continuous time counting process which has this property. Okay. That is why it is so important, and it is a good model as I said for radioactive decay, and it is a very good model for arrival of phone calls into telephone exchanges, all right. If a lot of people connected to us exchange, but only a very few people are actually making calls at any given time. So, if you look at the arrival of calls to a telephone exchange over some fixed period of time, it is reasonably well approximated by a Poisson process. Okay. So, it has many of these applications and it is analytically it has some very beautiful properties as we will see. Okay. Okay. So, I will stop here for today. Thank you.